the infinite square well, the one-dimensional infinite square well with Schrodinger's equation. So, I mean, this is the basic thing that you do in quantum mechanics. I'm not super great at quantum mechanics, so I forget things sometimes, and it's useful for me to make a video. So I'm going to make a video. What I'm going to do is I'm going to solve the Schrodinger's equation in one dimension for this infinite square well. I'm going to do a little bit of Python, in particular to normalize the wave function and to plot the wave function. I'm going to use Python. You'd be using Jupyter notebooks. But other than that, let's just get to the problem. So this is, when we get down to very, very, very small things, they don't behave like normal things do that we think about. If you throw a ball, and you can have it with any energy and any position and all that stuff. But at the atomic level, things don't work that way. Instead, what we do is to represent the object with a wave function. And so we have this capital psi, which I kind of wrote right there. And in one dimension, it could depend on x and t, and that's the wave function. Now, that's not something that we can measure, but what we can measure is the probability density, which is the complex conjugate of the wave function and multiplied by the wave function itself. That's the probability density. So that's what we could observe, and this gets down to probabilities. And I'm ruining all this stuff, all the background in quantum mechanics, and where this stuff comes from, and how this is the momentum operator, and this is the Hamiltonian, but I just want to solve it numerically instead of spending a lot of time on that. So this is the Schrodinger's equation. So this says I, which is the imaginary number, h bar is a constant, which is h over 2 pi, Planck's constant. The partial of psi with respect to t is equal to negative h bar squared over 2m. This is the del operator in 3 dimensions, but I'll write it in 1 dimension. Psi plus the potential psi. So in 1 dimension, it would look like this. I, h bar, the partial of psi with respect to t equals negative h bar squared over 2m partial the second derivative with respect to x of psi plus v psi. So that's the equation we want to work on. It is a differential equation, and we want to try to solve that inside of here. Now, what's important about this infinite square well is that it has an infinite potential right here at x equals 0 and at x equals a. So if the potential is infinite, and you look over here with an infinite potential, the only way that I can have a solution here is if psi of x and t equals 0 in these regions, in these two regions right here. So I can only have psi in here because it's an infinite potential. There's no way to solve that problem. Now, another thing that's important, because of the momentum operator dealing with the partial derivative with x, that means that psi has to be continuous. If it's discontinuous, you couldn't have momentum. And if psi is 0 right here, that means psi has to be 0 at these endpoints right here. Okay, we're going to use that later on. Okay, so let's go ahead and solve this equation. It's difficult because here we have a derivative with respect to t, a partial derivative with respect to t, and a second partial with respect to x. That's not easy, right? So what we want to do is if we can separate this function into a time and space part, that would be really great. So let me say this. I'm going to say capital psi of x and t is equal to some function of t times some function of x. Now I'm using the lowercase psi for the wave function that only depends on the x. Now let's put that in up here, and I get I h bar. Now I'm taking the partial of this with respect to t, but there is no t dependence here, so I can just pull that out front. So I'm just going to write psi partial of f with respect to t. Now over here I get negative h bar squared over 2m. Now I'm going to take the second partial with respect to x, but again, there's a time piece that just doesn't matter. So I'm going to put this as f, second partial of psi with respect to x. And then I have plus v f psi. And what I want to do is separate the variables. So I want to get, if I can get all the x stuff on one side and all the time stuff on another side, I'll be golden. So if I multiply this by 1 over f psi, both sides, Okay, then I'm going to get the following. So right here, I get I h bar. This side is going to cancel with that, so I get 1 over f, partial of f with respect to t. And over here, I get negative h bar squared over 2m. The f's going to cancel, so I get 1 over psi, second partial of psi with respect to x second. And then over here, those two cancel, I just get plus v. But we've done it now, because this part right here, let me get some colors. This part, this side of the equation, only depends on t. This side, assuming that the potential does not change with time. Okay, so here I'm assuming, I'll write that down in a second. This part only depends on x. And so this assumes v is a function, v, I'll write this as v equals v of x. It's not a time dependent, because otherwise it's a little bit more complicated. So, but mine doesn't change with time. So, but if this only depends on time and this only depends on x, the only way those two could be equal to each other, even though they're differentials, is that if they're both equal to the same constant. So we're going to set this equal to e. Both of these equal to e. Okay. So let's take the time part and set it equal to e, and then see where we go from there. So I have, if I just look at the time, I get I h bar partial 1 over f partial of f with respect to t equals e. That's my differential equation. And so this isn't too difficult to solve, right? Because this says, let's just solve this as the partial of f over t equals negative I f over h bar e. I should have written that backwards, but I divide both sides by h bar. I divide both sides by I, but divide by I is the same as multiplying by negative I. And then I multiply both sides by f. So this says, if I take the derivative of f with respect to t, I get, I should write this as negative I e over h bar f. I get the same function back, but this extra constant there. So what terms can I take where I get the same, I take the same derivative, I take the derivative, I get the same thing back, and that is the following. What if I say f of t is e to the negative I e over h bar t. So if I take the derivative of that, I get the same function back with this extra term in there. And I didn't put anything out front because we only need one constant, and I don't have to put it right here. We're going to have to normalize this. There could be a constant there, but I don't need to put that in there. So this is my function for energy. For time. That's my time function. Okay, now let's go to the space part. I'm going to go ahead and start on a new page just because I know it's going to get messy. So I'm going to rewrite this equation right here. So I have negative h bar squared over 2m, 1 over psi, second partial of psi with respect to x, plus v equals e. Okay, now I need to solve that. Now, inside the well, v equals 0. So that's gone. So now I can solve this in the same way. I'm gonna multiply both sides by psi and divide both sides by this term. So I get the second partial of psi with respect to x is going to be equal to negative 2m over h bar squared psi, or I'm going to put e psi. So let's just call this constant. Let's call this constant right here. This is just some value, right? Let's say k, just to make things easier. K is equal to, let's call that k squared. So k would be equal to, not the negative sign. So k would be equal to the square root of 2m e over h bar. And that's just to make our algebra a little bit easier. So now I have the second partial of psi with respect to x is equal to negative k squared psi. And you'll notice that this says I take the derivative twice and I get back the same function with a constant and a negative sign. And we've seen stuff like that before with the simple harmonic oscillator. So we know a solution can be written in terms of sines and cosines. You could use exponentials, but I'm going to use sines and cosines. So let's just say psi, and I'll check it, psi of x is equal to a sine kx plus b cosine kx. Now let's check that, because let's take the derivative twice. So the first derivative partial of psi with respect to x is going to be equal to a times the derivative of sine, which is cosine, and that take the derivative of the stuff inside, so it's going to be k cosine kx. Now I need to take the derivative of this. I get minus b k sine kx, because the derivative of cosine is negative sine. Now let's take the derivative again. Second partial of psi with respect to x is going to be equal to, okay, now I've taken the derivative of cosine, so I get another k, so I can get negative a k squared sine kx, and then I'm going to take the derivative of this. I get negative b, I get another k squared cosine kx, and this is equal to negative k squared times a sine kx plus b cosine kx. And so that is the same thing as psi. So it did work. Okay, but I don't know a and I don't know b. We can find those, and I don't know k. We can find those with our boundary conditions. So if you remember back over here, here's my square well, and this is at a. And so psi of 0 has to be 0, right? Because it has to be continuous right there. So if I put in x equals 0 up here, I get a times the sine of 0, which is 1, plus b times, I'm sorry, that's 0. Sine of 0 is 0. Plus b times the cosine of 0, which is 1. Now that's 0. In order for this term to be 0, the only way that can work is if b is equal to 0. That has to be true. Okay, so this whole term's gone. Now the other boundary condition I have is right here. I know that psi of a is equal to 0. So that's going to be equal to a, I don't have to worry about b, sine of ka equals 0. Well, if I put a is equal to 0, I do indeed get a solution. However, that's not really interesting. It'd just be it'd be psi is equal to 0, which works for the differential equation, but it's clearly not what we want. So the other way would make sine of 0. Sine of 0, sine is 0 if this term ka is equal to n pi. So I'm going to say ka equals n pi. And that's my constraint right there, and that's really important, right? Because if this is pi, I get 0. If it's 2 pi, I get 0. If it's 3 pi, I get 0. So this has to be true, where n is equal to 1, 2, 3, and so forth. Okay, so now we have a solution mostly. Oh, I need a piece of paper. So, but this also, remember that k equals n pi over a, but I know something about k, right? I know that k is equal to this before. K is the square root of 2me over h bar. So if I use ka equals n pi, then I get k equals the square root of 2me over h bar equals n pi. That's all in the square root. And one of the things I want to do is to solve for e, right? Because this is going to give constraints on e. So let's square both sides and multiply by h bar. I get 2me equals n pi, n squared, pi squared, h bar squared. So e equals n squared, pi squared, h bar squared over 2m. And that's my e sub n. I can have, again, n equals 1, 2, 3, dot, 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 dot. So I mostly have a solution now, except for one important thing. I don't know a. So here I have actually, let's write down the full solution because I think it is important. Psi as a function of x and t is going to be a sine kx, where k depends on n. I could put all that stuff in there, right? The e sub n. I don't want to do it though. Times e to the negative I. What was it? Where did I put it? I don't want to make a mistake. E negative I e over h bar t. And this, again, depends on n. So that's psi. Okay, what I want to do now is to normalize this, because I don't know a. But I do know that the object has to be found somewhere. So that means that this, negative infinity to infinity of psi star psi dx equals 1. Right? The probability of finding it between negative infinity and infinity has to be 1. Now, we already know that psi, this is only true for x between 0 and a. Outside of that is 0. So that means its integral becomes the integral from x equals 0 to x equals a of psi star psi. So let's go ahead and put that in here. So I get the complex conjugate of this is going to be a sine kx. I'm going to replace the I with the negative I. So I get e to the I en t over h bar. And then I have the same thing without replacing the I with the negative I. A sine kx e to the negative I en t over h bar dx. So this simplifies some. So I get the integral from 0 to a. I'm going to pull these two together, have a squared. These two terms multiply each other, have sine squared kx. Then I have e to the iet over h bar and times e to the negative iet over h bar. So these two multiply by each other to give 1. So I'll just get this. So I just need to integrate the sine squared kx dx from 0 to a. Now, I mean, it's not a super simple integral. I mean, we can do it, but I want to do this numerically and just to practice our numerical calculations. So how do we do a numerical calculation in Python? Suppose I have this function, and we'll do it for n equals 1. So here is x, and now I'm going to plot. This is psi star psi, and it looks like this. Remember, an integral is essentially the sum of, if I break this into tiny little pieces of dx, and I draw this up like that, I get a box, and I want to find the area of that box, and then I'm going to add up all these areas. So what I'm going to do is to break this into a bunch of small step sizes, and for each step size, let's just say d area, I'm going to use a again, is going to be psi star psi dx. And so if I multiply this by dx, I get that tiny little area. Now, here we do have a little bit of a trick, because you'll notice here that the psi star here and the psi star there are different. However, if I have a very small step, those two are very close together. So I can use just the first one. So now there's one other trick here that doesn't really matter. You can skip over it if you want. If I break this into a whole bunch of pieces and I go through all my x's, let's say there's 10 pieces. Let's say there's 10. How many areas would I have? If I break this into 10 x's like this, I actually have 9 areas, right? Because I can't take psi times dx for all of the psi's that I have, because then I'd have one extra area. if you did that and you broke it into 1,000 pieces, it wouldn't matter. But I'm going to do it with just one less piece. In Python, this is a little tricky. And I'm going to use Jupyter Python. So let me just jump over there and let's do this integral. Now, one of the things we're going to need to do is to pick some values because numerically I need numbers, right? So if I do this numerically, then I'm going to have some values. So let's just pick something simple like k equals kn is equal to 1. So we're at n equals 1, k equals 1. So all of that h bar squared stuff is going to be just all going to work out fine. Okay. So I'm really integrating sine from 0, and let's say a equals 1, 2. From 0 to 1 of 1 times x squared dx. That's one. No, not that. I was thinking about Python. Okay, so let's jump in and do this in Python. And if you haven't used Python before, some of the stuff might be a little weird, but you'll get it. I promise. Okay, so I have Jupyter Notebook right here open up, and I've already loaded in some modules. So one of the important things here is that Python by itself doesn't have things like sine. It doesn't have other features in there. You have to import those. So if I do, let's just say sine of 0.2, if I want to print that out, let's print, if I do sine of 0.2 and I run this cell, and I do have a thing down below, I'll link down below my intro to Jupyter Notebooks. It doesn't work because it's like, I don't know what the heck sine is. So when I import numpy, some people call it numpy, you call it whatever you want, it's your thing. I actually can say np dot sine. And now if I run that, it does indeed work. Okay, so that's what that does. The matplotlib.pyplot, that's for graphing, and we'll do that in a little bit. Okay, so let's delete this cell. So the first thing I'm going to do is I'm going to say, this is called area. Area equals 0. Because what I'm going to do is I'm going to calculate my wave function at a whole bunch of different points, and I'm going to add the area to this. So I need to have an area to start with. Okay. So now I'm going to generate my x values. So let's say a equals 1, k equals 1, kn, I should say kn equals 1. Now I'm going to generate my x values. Watch this. So x equals a range 0 to a 0.1. So a range is a function in Python that takes, there's several ways you can make this list. I could go through and just add up a whole bunch of points and add it to a list, but I don't want to do that. I want to do it the better way. A range makes an array of numbers between 0 and a with a step size of 0.1. So let's print this out, and I'll show you what I did. I did a small step size, so you can see. And I did arrange wrong. I don't know why I misspelled that. Oh, it's np.arrange. And there you go. So it splits these up. It goes from 0 to a by 0.1. And now there are other ways to do this, and people debate about which one's better, but it doesn't really matter if you have a large number, so just trust me. So if I do this as 0.01, then and run it, I don't want to do that, but I did it anyway, then I get 100 numbers, and that's fine. Okay, so now what I'm going to do is I need to calculate my psi values. So let's say psi star, let's just call this p because it's psi star psi. P is going to be equal to np.sine of k times x squared. And this is what's so great about using an array. I can do this. Let's go back up here and put this at 0.1. And now let's not print this out. Let's make our other values for psi star psi and print that out. And run it. And it did not work. Kn. I call it Kn. And there you go. So it took each value of x, it found the sign of it, it squared it, and it returned the value. So I don't have to go through and do anything complicated. I now have a list of x's and p's, and I can calculate the area. So I already have area 0. So I'm going to say the following. This is not the best way to do it, but for I in range len of x minus 1. Let's just print out I. So this goes through 0 to 8, right? It starts at 0, it doesn't go all the way through, and it prints out a number, I. And this says, what's the length of that value x? Subtract 1, and then go through that range. Now, what if I did this? Print x, I. So now I can print out each x value, and I did that. I don't do them for all of them because I don't include the last one. But now I can reference each one. So I can go up here and say this. D area equals P I times, actually I should go up here and call this dx equals 0.1. I'll put this as dx. I don't need to calculate the change in x. I already know what it is. And that's my differential area. I take my psi, I multiply it by my my width of my dx, and that's the area of that one little piece. And then I can find the total area just by adding that on. And now I'll print that out. And there I get it. And of course, I use a very large thing. And I actually know, let's put this, area equals, it should be equal to the square root. I'm using this I'm going to write an equation for this. The square root of 2 over a, I think it is. There. So let's see if that, so it should be the square root of 2. So if I just print, because my a was 1, square root of 2, oh, I got to put numpy. And I get something different. Is it a over 2? Square root of 2 over a. That's what I put. Oh, that's a squared. This is a squared. So I need to actually, so it should be a squared. If I, that area is a squared. No, that's 1 over a squared, right? That's the area, and I want to set that equal to 1. Let me switch back over here so I can show you what it is. I made a mistake. So this is actually a, and I want to set that equal to 1. So if I say the integral of sine squared k x dx equals 1 over a. So whatever value I get for this is going to be 1 over, and this is a squared. A squared. So a is going to be the square root of 1 over the area. So that was my mistake. So let's go over here, back to this. And I'm going to say a equals, what did I just say? Square root, np dot square root, 1 divided by area. And then I'm going to print that. And let's see if that works. And I get something different. And let's just see if I change this step size. There. Okay. So as you notice it was really way off. And that changed the step size to 0.01. Let's change it, make it even smaller. Oh, it still didn't change. Square root of 2 over a. No. I can't remember. I feel like I'm making a mistake. I know a is equal to the square root of 2 over a, and I made a mistake. Okay, I'm going to come back and fix this mistake. I could have just integrated sine, and I just didn't want to do that because I was like, hey, I'll be cool. I'll be like the cool guy that doesn't Python, and then I made a mistake. Okay, So, but let's do the following. Let's say that a is square root of 2 over a. I'm pretty sure that's right. So I have my wave function. I want to plot the first and second energy levels. So let's do this. Let's say x. I already have x. Let's calculate psi. Psi is equal to, I'm going to say a. A equals square root of 2 divided by a. I think that's right. And then I can say psi equals a times sine. Oh, I need n. Let's do this. N equals 1. And then k, ooh, I made a mistake. Because I put k in, I put the n inside of there. Let's just proceed with n equals 1, and then k2, I'm looking at my values over here. What did I put for k? I told you quantum mechanics wasn't my strong suit, right? I'm just making some silly mistakes. So it'd be k is 1 over n squared. So for k2 would be 1 over 4. Okay. So let's just plot this. Yeah, let's just plot it. And then I'm just going to plot psi 1. So let's say psi equals a times sine kn times x. That's it. And then I'm going to plot that. So I'm going to say, this is pretty easy actually, plt dot plot x psi, plt dot plot show, or grid, dot grid. I can give it x labels too, plt dot x label, I think that's what it is, x, plt dot y label, psi, and then plt dot show. I think that'll work. No. Oh. Oh, gosh, I made a whole bunch of mistakes. There we go. But that's not right. From 0 to 1, NP I said sine k a. Oh, I didn't normalize it, but still it should be fine. No, I did normalize it. Let's just put a. What if I put a equals 1? Kn times x. Why isn't it going back down to 0? I did this before. Okay, I think I've felt like I've made this long enough and enough errors. I'll correct this and make another video at some point. But I'm kind of off a little bit here, so I'm just going to stop. I will post this because the first part I think was really good. I think this calculation I'm doing something wrong in Python. So there you go. I will make another video. I promise.